my name is Xinshuo from NVIDIA Autonomous Vehicle Research. Today, I'm going to share about our work on the scalability of modular autonomy stacks. And this is a joint team effort across multiple members in our group. And I would really hope to see everybody around in person, but unfortunately, I couldn't come in person, so I will have to give this presentation remotely. Okay, so let's get started. By the way, is my screen sharing working?
Yep.
Yes, it's working.
Okay, sounds good. So broadly, there are two main architectures for vehicle autonomy today. On one hand, modular architectures, which comprise independently trained modules. For example, for detection, tracking, prediction, planning, and control, this is the typical structure in the past decades because of the key advantages such as interoperability, reusability, and feasibility to make formal safety claim. However, this architecture introduces information bottlenecks and might give rise to integration challenges. On the other hand, we have monolithic architectures with end-to-end learning, which typically link perception to control through a neural network, and only implicitly encode key capacities such as object detection, mapping, and agent prediction. As key advantages, an end-to-end architectures remove information bottlenecks, and because of that, one could argue it might achieve a level of optimality unattainable by modular architectures, which are based on rigid module decomposition. Also, it's straightforward to scale up the performance of the end-to-end architectures when large-scale data becomes available nowadays. The claim that the end-to-end stack may achieve performance unattainable by modular architectures seems to be supported and corroborated by empirical evidence. Taking the well-established Carla driving challenge as an example, when the pioneering work, learning by cheating, was first proposed, its performance is relatively low due to the poor quality of the expert and also data collection process. However, as time goes by and stronger experts are developed nowadays, performance of the subsequent work in end-to-end AV stack has been substantially improved. In contrast, if we look at the popular modular stacks, such as Pilot and Tech for Edge Car in the Carla closed-loop driving challenges, the performance really lags behind and does not benefit from the improved data and expert over time. So the question is that, can we conclusively argue that modular architectures are fundamentally suboptimal? Well, the answer is not quite. Let's consider a standard decision-making setting where we want to control a system with state X by controlling the action used based on the measurement states. Define the information vector or the input as the history of measurements and the control up to the current frame. The problem is to find an optimal policy that maps the information vector into control actions and optimize the performance given a cost. One can show that the conditional state distribution from the information vector to the state, denoted by P here, is a sufficient statistic, and the optimal controller can always be written as a mapping from the conditional state distribution to control actions. And explicitly, this means that we can decompose the optimal controller into two parts. One, the estimator, which uses the current measurement and the previous control values to update the distribution P, and the actuator, which generates the control input as a function of the distribution P. This interpretation has formed the basis for various suboptimal control schemes that separate the controller into an estimator and an actuator. But importantly, we would like to argue that the suboptimality of these schemes stems from the suboptimal design of the individual component rather than the modular decomposition itself. Inspired by this theory, we believe that the standard decomposition of the modular AV stack should not lag behind too much in terms of the performance in a closed-loop setting. And it might be because of this, because the suboptimality of individual components causes the performance gap compared to the end-to-end stack. To verify this, we went back to the Carla driving challenge and paid particular attention to design different modules with state-of-the-art techniques. For example, we use the state-of-the-art transformer-based architectures such as Data 3D, Filter 3D for detection versus the 2D detection method used in Pilot. Similarly for tracking with more recent 3D trackers such as Modular 3D, whereas Pilot used the old 2D trackers such as Sort. Also for prediction, we support the interaction-aware multimodal trajectory prediction methods such as Agent Informer and Trajectory++, rather than the older method that predict trajectory for each agent independently as in Pilot. And notably, our AV stack is built on top of the very recent MM3D community that provide the state-of-the-art training regime and infrastructure, data augmentation, and so on and so forth to allow the best performance for building the entire AV stack. Without much surprise, our modular AV stack with the state-of-the-art techniques significantly improved the performance over the prior modular stack, such as the Pilot. This is expected because we equipped our stack with the state-of-the-art components and also MM Detector 3D framework, as I said earlier. But what's more interesting is that our modular stack with independently trained modules also outperformed the very recent end-to-end stack in the Carla closed-loop driving challenge. They could include learning from all vehicles, TCP, and interfuser. Here, we use the pre-trained weights released by other teams and ran the apple-to-apple closed-loop comparison in the offline leaderboard using the official testing routes, scenarios, and the metrics. Also, if we replace the perception modules with the privileged information from the simulator, the rest of our modular stack, aka our expert, can achieve a near-perfect score close to 100% in a Carla closed-loop setting. Again, this confirms that the suboptimality of the modular stack stems more from the suboptimal design of the individual component rather than the decomposition of the key modules. Also, this result suggests that there is still a huge room for improvements of the current end-to-end stack with imitation learning or reinforcement learning. For example, better design of the stack, better data, or training regime. And in fact, our expert stack could serve as a performance expert to further augment the research in end-to-end AV stack. Moreover, this might imply that we need to have a better closed-loop driving benchmark, such as NVIDIA DriveSim or the Webis Unisim as introduced by Raquel just now, as well as the metrics for the full stack closed-loop evaluation. Here are some video demos for our stack running in the Carla closed-loop setting that can handle various challenging scenarios. For example, taking over vehicles that are malfunctioning, passing through unprotected left turns, and conducting highway lane changes, and also negotiating at unsynchronized intersection, and so on and so forth. So as we have seen, modular stack works, and if designed properly and keeping up with state-of-the-art techniques, it can even outperform the top end-to-end stacks. However, we always weaknesses, such as the information bottleneck, especially during training, as modules are not learned jointly, and even some modules are not data-driven, and therefore the entire stack could not scale with the data. So how could we improve that? To scale the performance with data, a lateral question is whether we can get the best of both worlds in terms of the architecture designs, right? In other words, combine the modular stack with the monolithic end-to-end design. We believe the answer is yes, and to this purpose, we are developing modular and end-to-end differentiable AV stacks that keep the main modules of a traditional AV stack and at the same time can be trained jointly from data. There are emerging ideas from two architecture paradigms. The key idea is to implement existing modules in a neural programming framework where all computation is expressed at a single differentiable computation graph. This differentiability allows us to backpropagate gradients through both neural network components as well as the fixed computation blocks, such as classical planning algorithm, and this way we can perform gradient-based end-to-end training, improving upstream modules directly for downstream tasks. So how can we make our AV stack differentiable? And obviously, neural networks are already differentiable. This is mostly seen in the perception. But we can also make many algorithms, such as in the planning and state estimation, differentiable as well. Specifically, we can express any algorithm as a computation graph, and as long as all operations are differentiable, we can backpropagate through the algorithm to any learnable parameters or inputs of the module, same as neural networks. The only caveat is that we need to design the differentiable operation within the algorithm. Fortunately, recent work has introduced various ideas to approximate useful gradients for such non-differentiable operations, such as approximating max with softmax, reparametrizing Gaussian distributions, and approximating Hungarian algorithm with differentiability for tracking, and in some cases, approximating gradients for any black box optimization problems. Using these ideas, differentiable variants of many classic robot algorithms has been developed in the recent years. For example, for state estimation, like Kalman filters and particle filters, and also differentiable planners, like for MDP and POMDPs, and also differentiable control algorithm and optimizers. I have a list here only for a subset of the relevant works, but the list has been growing since. Okay, to make the ideas more concrete, let's focus on the prediction, planning, and control modules. This is an interesting setting, given the importance of these downstream tasks, as well as the fact that this pipeline comprises both data-driven components, for example, for prediction, and also classic algorithm for planning and control that are typically not differentiable. Specifically, we started with a fairly standard modular architectures, and it has a deep prediction model or data-driven prediction methods such as trajectron plus, which consumes past tracklets for all agents on the road and output probabilistic distributions about their future trajectories. These predictions are fed into a planner, a sampling-based algorithm that generates a set of candidate trajectories, and we score them based on handcrafted cost function, and then select the candidate with the lowest cost. The trajectory is further optimized with the optimization-based controller module, specifically an iterative LQR algorithm. And conventionally, the modules are developed independently, which means that the prediction model is trained from the driving data to maximize the prediction accuracy, while the planner and controller are handcrafted. The key feature of our differentiable stack is that the planner and controller algorithms are differentiable. In the planner, we relax the argument operation with the sampling, and in the controller, we use differentiable MPC from prior work. And during inference, our work behaves exactly the same as a standard stack, but what the differentiability allows us to do is to use data at the end of the pipeline, backpropagate the noise through the control and planning algorithm, and train a prediction model so that it can focus more on the predictions that are critical for planning. Specifically, we use a standard variational elbow loss for the prediction model and a cross entropy loss for the planner and a hindsight loss for the controller. The hindsight cost is effectively like a reward in RL. It measures the plan quality in hindsight after observing the future behavior of other road agents, which we didn't know at the planning time. We benchmark our method on standard nuisance driving datasets, and we compare two architectures: the standard one that trains the prediction model to minimize the prediction error, and also the deep stack that trains the prediction for a combination of prediction planning and control losses. And we measure the prediction performance through the standard ADE and the planning performance through the average cost of the ego trajectories. We present cost as a percentage difference compared to an oracle that plans with perfect ground truth prediction knowledge. While the two stacks perform similarly in terms of prediction error, we observe that deep stack achieves substantially better plans, reducing the average cost difference to the oracle from 29% to 17%. It's important to highlight that the two stack perform the same computation as inference time, and the difference is that the deep stack train its prediction to be more useful for planning and control algorithms. In concrete examples, we found that deep stack yield less spurious predictions, which would otherwise be critical for the downstream planner. All right. So far, I've been talking about the joint training of modular stack with some form of supervised data, but labeling data for AV can also be very expensive. We have seen an incredible success of foundation models recently in generative AI, both for image generation and language models that learn very powerful representation for a massive amount of unlabeled data. So we're also working on the potential, we're looking at the potential of the unsupervised representation learning in modular AV stacks. The first question is, why do we need learned interface or learned representations? The most common interface to connect the perception and planning is bounding boxes. Perception models output a discrete bounding boxes set, followed by a tracker to associate the bounding boxes across time, which is used in almost every autonomous driving pipeline. The limitations are, however, the detectors struggle with real objects not well represented in a dataset, arbitrary shapes that are hard to be expressed as a bounding box, and the bounding box also contain very little information. So an interesting alternative we're looking at right now is to model the environments through an occupancy voxel with the learned semantic representations. Occupancy voxel can model arbitrary objects, including objects not in a dataset, and it can also provide more accurate geometry, leading to better occlusion reasoning, planning, and so on and so forth. If we augment these voxels with learned features beyond simple occupancy, we can retain much more useful information for the sensors. Let's first look at how we learn this occupancy representation. At the core of our proposed method is generalizable neural rendering. Neural rendering, originated from computer graphics, provides a convenient way to link 3D representations such as voxels to 2D images that we can observe. And the core idea, or specifically, the core idea of our neural rendering is to represent the scene with 3D occupancy and color fields. Then a neural network can query this 3D representation and differentiably render pixels by aggregating color information along each rendering ray. We want to leverage this volumetric rendering to self-supervise a learned 3D representation. Our method inputs multi-view images, passes them through image encoders such as Redslate or transformers. The encoded 2D features are lifted into 3D with implicit depth estimation. Finally, these 3D feature voxels are rendered by volumetric rendering to generate original images for the current time step or future time steps. A very strong advantage here, and the reason why this representation can scale, is that we can learn it from self-supervision only using sequence of sensor data. Additionally, we can also distill pre-trained foundation model features to these 3D feature voxels, such as from clip or download features. Here are some preliminary results. We can generate novel views based on the new camera geometries. Based on new camera trajectories. Most importantly, the learned representations lead to consistent depth and semantics across time as shown in the video. Also, thanks to the clip features, our model enables open vocabulary scene manipulation. For example, we can query the 3D representation with language prompt to remove backgrounds and only keep cars. This is done by finding the corresponding voxels to text via nearest label search in the feature space. We're now working on building a planning architecture on top of it. We envision this representation learned via self-supervision can further scale up the performance of our AV stack. So that's it. So I'm going to just quickly conclude what we have discussed here. Mainly, there are 3 points. First, we show that the modular decomposition of the AV stack is still a valid design, right? And modular architectures can work really well in closed-loop driving if designed properly. Second, I talk about how we can make modular stack differentiable and therefore making them scale with data and joint training. This architecture, while still modular, ensures safety and interoperability by certifying each submodules independently. And finally, in the era of big data, the significance of neural representation cannot be overstated. Our intent is to learn these representations from data, capitalizing on the emerging property of self-supervision. We assert that these learned representations are integral and complementary to our end-to-end AV architecture. That's it. All right. I would like to thank everyone for listening and also organizers for the invitation. I'm now open for some quick questions if there are any. But for additional inquiries, feel free to visit our website as well or reach us directly. Thank you.
Thank you very much. We have some time for questions. Anybody?
So I have a question.
Remotely.
Yeah. Is the question in the chat?
Yeah. I have a question. So when you talked about like the multiple camera representations and you are lifting it to implicit depth, could you talk a little bit more about it? Like, firstly, I'd like to know if you can talk about like the reference frame that you're using. Like, because right now we are using multiple cameras, so are you using like a ground reference frame to lift it? Could you talk more about that?
Yeah, I guess here for the implicit depth representation, we're saying that we're just doing the standard 2D to 3D lifting. I mean, you can do explicit as well. There are multiple ways of lifting the 2D feature to 3D or to BEV. This is quite common in the, I think, in the BEV
Yeah.
perception. Yeah.
Sure, I understand that. So, but you have to when you're lifting it, you're using like a common reference frame, right? And is that
Yeah.
reference frame in the like centered at the ground somewhere on the car, or
Yeah.
is it like some camera? Yeah.
I think we're using the ego coordinates.
Ego coordinate on the ground though, right?
I guess that depends on data set, right? So
I
ego
see.
coordinates, it could be in the center of the vehicle or it could be on the ground. I guess it's just like a transformation, right?
Okay. And one last question.
Yeah.
So like representing road topology, how are you actually how are you actually predicting road topology? You can talk more about that. I know it's a more open-ended question, but
Yeah, definitely. So I guess that's the, I mean, there is a lot of active research right now in that for doing online vectorized mapping or online HD map construction. So far in the modular AV stack that I just discussed, we're actually still using an offline HD map, meaning that we're using the HD map provided by the Carla because we are running the Carla challenge, right? And there is a map provided there. But we definitely are looking to doing the vectorized HD map generation as well. And I personally believe that this vectorized representation could be more integrated into our AV architecture, especially I've seen like better performance. If you look at the recent work from the vectorized VAD paper, I think that's the way to go. But of course, there's a lot of a major body of work in using segmentation-based mapping, segmentation-based method for doing online mapping as well. I guess it's quite open-ended right now. It's still unclear which way will lead to better performance for downstream planning. And that's where we should go, right? To really connect the planning with the online mapping to really see what we really need from the online mapping in order to improve the downstream planning performance.
Gotcha. Thank you so much.
Yeah, I guess that's also one of the goal of our work in making this entire AV stack infrastructure so that we can really doing some innovation for the full AV stack. We'll at least understand better how we can improve the upstream module so that it can more useful for the downstream. Otherwise, we're just developing individual modules isolatedly, and it's really hard to get the improvements on the online HD mapping alone, or what's the real or the most important factor that could contribute to the downstream.
Understood. Thank you. Thank you so much.
Yeah, thanks for the question.
Any additional questions? Yes, I guess we can